Hello and welcome back to Chemistry from Jay's house. I didn't collect homework, I didn't go over homework. Now I know what you guys are thinking. Jay sure talks a lot, but what's the point? What is the point? Okay, let's go to the top right. Let's write the date. I believe this is supposed to happen on the 20th. As usual, check that is the right date. If not, write the right date. Skip a line, go all the way left, write the point. And the point today is how are pressure, volume, and temperature all related for a gas. So, and there's a law for this, and the law is called the combined gas law. So if you're doing physical notes, skip a couple lines. It is called the combined gas law, and we'll talk about how it got its name. But it is P sub 1 V sub 1 all over T sub 1. So that's actually a mathematical phrase saying that P, the initial P, times the initial V, all divided by the initial temperature, equals P sub 2 V sub 2 all over T sub 2. So if you start with a gas and you know the initial pressure and you know the initial volume, you multiply those together and then you divide that by the initial temperature. Then something happens. It heats up. It goes into a bigger container. It changes, you drop it 10,000 feet under the sea. Then in the new situation, so let's say this started at, room temperature, 1 atmosphere, so at, sea level, and you have, 1 liter of gas. After you take that 1 liter of gas and you take it down to, 1,000 meters under the sea, right? And you want to say, okay, I know the pressure, I know the volume. What would the temperature be? Well, you would take the pressure times the volume, and all that divided by the new temperature would equal whatever it was before. So we'll talk about what that means, but this is a mathematical equation. You would put actual numbers in there, you would pull out an actual calculator, and you would solve for this. And we will dissect it, fear not. But I want to talk about a couple quick things that you already know. Like one thing is, you already know how pressure and temperature are related. As pressure goes up, temperature goes up, and vice versa. As temperature goes down, pressure goes down. And the person who figured that out had the last name Gay-Lussac. And you already know how volume and temperature react. As volume goes up, temperature goes up, and vice versa. And the person who thought of that had the last name Charles. So PV over T, we know how P and T work. We know how V and T work. The only thing that's left is, what about P and V directly? What about to each other? How those relate to each other? That's how we're going to start today's class. So if you haven't, pause the video and write this all down. Pause. Welcome back. So now all we have to figure out is how we know how pressure and temperature are related. They're directly proportional. We know how volume and temperature are related. They're directly proportional. But we don't know how pressure and volume are related to each other. So to understand that, we have to learn about a third scientist. And this third scientist had the name Boyle. And Boyle's law says that pressure and volume are not proportional, does anybody know what the opposite of proportional is? That's right, inversely proportional. Well done. What that means, inversely proportional is the exact opposite. If pressure goes up, volume goes down. So pressure and volume, they go, oops, turn that around, like that. As the pressure increases, the volume goes down. As the volume increases, the pressure goes down. And we'll talk about that right now, and then we'll tie all three, Gay-Lussac's law, Charles' law, and Boyle's law, all together into the combined gas law, and that will be class. Now, to understand this, let's get my Kevlar balloon that doesn't really exist out. Ooh, incredibly poorly drawn. Thank you. And again, we'll attach it to the wall so we don't have to worry about it flying off. And we talked about how there's particles, they're banging around and that sort of thing. But now what I'd like to talk about is I'd like to talk about not temperature, not how much the inside is moving, but I'd like to talk about the pressure from the outside. So we're going to have some air particles. Again, that's going to be nitrogen molecules, oxygen molecules, carbon dioxide molecules, that kind of stuff. And those particles are, of course, banging around. They're all over this balloon. So they're banging, and we'll say that they are hitting, more or less, room temperature, whatever room temperature is, amount. Which means, basically, they're all moving the same speed. And they're banging on the balloon. And the reason the balloon is that size, right, is because it's at this size that the inside is banging against it just as hard as the outside is banging against it. So the particles on the inside, they are also banging, right? And if the balloon is not changing shape, then what we would see is a balance between how much the particles on the inside are banging and how much the particles on the outside are banging. And if the balloon is not changing shape, then they're banging just as much. These guys are banging outward as much as these guys are banging inward. Okay, so that's going to be our first state. Okay, now what happens if we increase the pressure? And when we say increase the pressure, we mean from the outside. We mean increase the kinetic energy of the particles from the outside. So instead of going this fast, they're going that fast. Instead of that. I mean, these things are really bringing it. We gave them a bunch of Red Bull, or we just pressurized them. And they are now really banging into this balloon. What's going to happen to the size of the balloon? Well, on the inside, there's no change. The red particles are banging around just as much as they always were. But the ones on the outside are, oh God, take that balloon, take that. You owe me money. Give me that balloon, right? So what's going to happen to the balloon? What's going to happen is the balloon is going to shrink. It's going to become a smaller balloon until, again, the particles on the inside and these particles on the outside, which are going to push it in. Bam, take that. Bam, take that. Ha ha ha, we have more power. We've been pressurized. Woo! I'm going to shrink the size of your balloon. Yay! So as pressure increases, as the particles on the outside get more power, and bang against the balloon harder, the ones on the inside lose ground. And the whole thing collapses. And that's why you can jump on YouTube and you can look at things in pressure chambers. You know, the classic is like the foam head that, you know, gets really, really small. Or you can see things going underwater, right? That's another thing is people will dive down and they'll just watch like things like crumple. It's really fun to watch styrofoam crumple at pressure, right? And the reason it works is the internal particles have the same amount of energy. We're not changing them at all, but we're banging against them harder. So they're just going to lose ground and it's going to shrink. Okay, that sounds well and good. What about the other direction? I 100% believe now that if I increase the pressure, if I bang harder against the balloon will shrink. But what if I go the other way? What if I lower the pressure? Well, let's get our balloon. Again, poorly drawn. You're very welcome. And there's particles banging on it. And we'll take it back to room temp. So the particles are basically again, the particles on the inside are banging just as hard as the particles on the outside, and the balloon will stabilize. That'll be the shape and size of the balloon. But now what we do is we take it into space. Yes. And what that means is we're going to lose some power from the outside. These guys are going to bang less. They're going to bang a lot less. What if we depressurize it? Now again, before we changed, these guys were banging just as hard. Now these guys aren't banging as hard, but the ones on the inside are. What's going to happen? Way, we get a chance to win, woohoo! They're going to actually gain ground because these guys aren't changing how hard they're hitting. And if these guys hit the same amount, well, then the balloon stabilizes. But if these guys hit less, then these guys are actually going to win some ground. And what we would end up seeing is, instead of the balloon collapsing, we would see the balloon expanding. Because now, again, these guys aren't losing any energy. We're not changing how fast these guys are moving. Their arrows are basically the same length, but these particles in the outside, that's kind of long. These particles on the outside are losing their power. And so now the red gained, the internal particles are going to gain ground. These guys are going to win, and it's going to keep expanding until however much these guys bang equals how much those guys bang. And now what happened to the volume? It got big. So as the pressure on the outside drops, as we bang less on the outside, these guys can spread out more until they equalize. So the volume would increase. And by gum, look at that. That is the definition of inversely proportional. As one goes down, the other goes up. And as one goes down, the other goes up. That is what inversely proportional looks like. Right? So pressure and temperature, proportional. Volume and temperature, proportional. Pressure and volume, wah, 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 inversely proportional. Now let's talk about why mathematically. We have seen it, why in the real world, why this makes sense. It jives with the things that we know and have experienced in our lives. And all science needs to jive with the things we actually experience. If we have the perfect mathematic formula, but it says that gravity doesn't exist, then that's a bad formula. So let's go back to the combined gas law. So this here is at the start. We can measure the pressure, we can measure the volume, we can measure the temperature of a gas at the start. Then we change something. Something changes. What changes? I don't know. We increase the pressure, we lower the volume, we increase the temperature, we just muck with one of these. And then the question becomes, now, how does everything pan out? So this is at the end. So at the initial, we take all of the measurements that we want because nothing's happened. This is the beginning. We can predict what the end will look like, right? Because I say, hey, if I'm going to increase the temperature by so much, by 20 degrees Kelvin, how's the pressure going to change, or how's the volume going to change? Well, we know that if I increase the temperature, if this goes up, pressure goes up too, because we know that those are proportional. We also know that those are proportional. And we just found out that pressure and volume are inversely proportional. Now, mathematically, how does this formula imply that? Well, now we got to jump into just a smidge of math, and then I'm going to give you a phrase that makes it so you don't need to know any math whatsoever. You're welcome. Okay, so if I, let's say, double, and I'm going to use this space. What this says, by the way, is these are equal. If I multiply the pressure and the volume, divide it all by the temperature, before, no matter how I mess with it, no matter which of these I muck with, if I multiply the new pressure times the volume, divide that by the new temperature, those actually are going to equal the exact same number. So I can do some algebra and solve for stiffs. So let's start, I don't know, we'll say double the pressure, right? Okay, so what if the pressure doubles? So I'm mucking with just the pressure. But I'm not going to change the volume or the temperature. I'm just mucking with the pressure. Now I'd like to know